In 2006, scientists attached a satellite tag to a female leatherback sea turtle on a beach in Indonesia. What happened next would challenge almost everything we thought a reptile should be capable of. The turtle began on a remote beach in Papua, Indonesia, and then pushed into open water. She traveled past the scattered islands of Papua New Guinea, across the vast emptiness of the Western Pacific, skirting the equator, then continued on, past nothing but water, for thousands of kilometers. At one point, she passed near Hawaii, one of the only landmarks in an otherwise featureless ocean. And then she kept going, across an entire ocean basin, through cold, shifting currents, until finally, after months at sea, she arrived off the coast of Oregon. The turtle had traveled 20,558 kilometers, or 12,774 miles. The journey took the intrepid turtle 647 days to complete, and the only reason the scientists stopped tracking her was because the signal was lost. It's possible she kept going. The scientists had just recorded the longest migration of any marine vertebrate on Earth. Farther than sharks, farther than any type of whale. Why would a turtle travel so unbelievably far? And how would it know where to go, especially when the vast ocean is almost completely featureless? Then, in 2024, scientists were tracking a leatherback sea turtle near the Solomon Islands, this time tracking not just its position, but its depth. At first, the turtle seemed to make a few normal, shallow dives, about what you'd expect for a cruising turtle, occasionally dipping down to find prey. And then something crazy happened. It started to plunge deep, really deep. A 100-meter dive turned into 200, then 300, 400, and it kept going, into total darkness, past 1,000 meters, where no light penetrates. And it kept going still, down to 1,344 meters, or 4,409 feet, well within the bathypelagic zone. Why on earth did this turtle suddenly decide to dive to the pitch-black depths of the sea? These two stories highlight something important: that the leatherback sea turtle is not a normal turtle. When we think of sea turtles, we picture the sunny shallows, turtles swimming through sunbeams with their cute faces and hard protective shells. We might picture Florida or Hawaii on postcards with palm trees. But if we were to make a postcard with a leatherback, it might be more fitting to have it in the icy waters of Norway or in the dark depths of the sea. Because leatherbacks routinely travel farther north than any other reptile on Earth, and some have even been recorded beyond the Arctic Circle. They are the most widely distributed reptile on Earth, with a massive global range. And despite being turtles, they don't even have the thing turtles are most famous for. Instead of a rigid shell, their backs are covered by a thick, leathery skin. Their scientific name actually translates to skin turtle. And amazingly, they achieve all of their extreme feats on a diet of one of the least nutritious foods you could ever come up with. Everything about them feels wrong. Wrong for a turtle, wrong for a reptile, even wrong for an animal. And so many parts of their anatomy are like nothing else I have ever seen. Like a bony covering made of thousands of articulated joints, or this pink spot on their head that is crucial in their migration behavior. There's a crystal inside their brain that connects them to Earth's tectonic plates, and maybe even symbiotic magnetic bacteria. There is simply no other animal on Earth like a leatherback. So how does a reptile dive into the dark reaches of the ocean's abyss? And how does it live in waters cold enough that it would kill most mammals, let alone reptiles? How and why do they regularly travel across the entire planet? And what ancient force compels them to live a life this extreme? Leatherback sea turtles are the largest living turtles, and the heaviest reptiles that regularly roam the open ocean. An adult leatherback can exceed 2 meters in length and weigh more than 600 kilograms. The largest leatherback turtle ever recorded was a dead, stranded male on a beach in Wales. It weighed 916 kilograms or 2,019 pounds. And females get bigger than males, so the true upper limit is likely bigger than this. They are the only surviving member of the ancient sea turtle family called Dermochellidae, and have remained relatively unchanged since they first arose 65 million years ago. They are swimming relics of a much older ocean. The 6 other types of existing sea turtles are considered the modern sea turtles. These have the classic turtle design, a rigid domed shell made of fused ribs and vertebrae, keratin scutes forming distinct plates, and a relatively compact, armored body plan. But the leatherback has none of these typical turtle features. Its carapace is covered in thick, oily flesh and flexible leather-like skin instead of a rigid shell. It's more like tough neoprene than armor. Its body is streamlined rather than domed, and running lengthwise from head to tail are 7 pronounced ridges instead of distinct plates. But this still puzzles me. Why would a fleshy shell be an advantage over a hard shell and persist in this same form for over 65 million years? A hard shell protects from predators. A fleshy one seems to leave these turtles vulnerable. The answer begins not with predators, but with pressure. Leatherback turtles are the deepest diving reptile on Earth. They regularly descend hundreds of meters and sometimes, as we heard at the beginning of this video, dive beyond 1,000 meters into the dark, cold bathypelagic zone. A green sea turtle, for comparison, can dive to only around 110 meters. If a green sea turtle with its rigid shell went as deep as a leatherback, it might not get all the way ocean-gated, crushed by the pressure to the point of implosion, but it might crack. What makes the leatherback sea turtle so much more capable of swimming at these depths is their fleshy carapace. Beneath its thick, rubbery skin is not a single solid dome, but a mosaic of thousands of bony plates called osteoderms. And the edges between them are not smooth. They are jagged, shaped into a zigzag of interlocking extrusions and intrusions, which is called a suture geometry. This creates stiffness while still permitting motion. In leatherbacks, these osteoderms can flex around each other at roughly 15 degrees. These are genuinely articulated joints. So when a leatherback dives to depths greater than 1,000 meters, the surrounding pressure compresses the lung cavity and the carapace can yield with it. I don't think submersible engineers have copied this design yet, but maybe they should. It's certainly better than carbon fiber. But even with this structural resilience, surviving these depths for long periods of time is profoundly physiologically demanding. It requires specialized anatomy that should be impossible for a reptile to possess. When a leatherback submerges, its heart rate drops dramatically to just 1 beat per minute, a response known as bradycardia. This reduces oxygen consumption and prioritizes blood flow to critical organs. They can hold their breath for 85 minutes when actively diving. Other reptiles can slow their heart rate underwater, but leatherbacks take this much further. They also have large blood volume relative to body size, high hemoglobin concentrations in the blood, and well-developed muscles rich in myoglobin, which allows oxygen to be stored directly inside the muscle tissue, essentially turning their muscles into oxygen tanks. High myoglobin concentrations are a hallmark of diving mammals like whales and seals, not reptiles. So all of this means that they don't just rely on lung air like most reptiles do. Most of their dive oxygen is stored in blood and muscle, which are less compressible under pressure. You can see just how much more of their oxygen is stored in blood and muscle compared to a loggerhead sea turtle. But after an hour or so at depth, the leatherback must return to the surface to breathe. But there's a problem here too. At these depths, leatherbacks are negatively buoyant. If you've ever been scuba diving, this is a sort of terrifying phenomenon to think about. You're at the deepest part of your dive, almost out of air, and your weight belt is holding you to the bottom. You can't drop your weight belt, and there's no BCD inflator to save you. All you can do is vigorously kick and hope you can battle these gravitational forces. This is sort of a leatherback's reality, except for one incredible adaptation: those unique ridges on their carapace. This 2016 paper is unexpectedly cool. Scientists wanted to understand what role these ridges play in the hydrodynamics of a swimming leatherback. So they constructed 2 different carapace models of a leatherback, one with ridges and one without, and stuck them in a wind tunnel. And the results were surprisingly dramatic. At certain swimming angles, the ridges reduced drag by as much as 32%. But the weirdest part was how they did it. Instead of smoothing water over the shell, the ridges actually created tiny vortices, spinning tubes of water that acted like invisible guides. These vortices kept the flow attached to the turtle's body for longer, preventing it from peeling away and forming a turbulent wake behind it. And amazingly, during steep upward climbs from deep dives, these ridges increased the lift, essentially giving them more upward movement for the same effort. So these leatherbacks seem to have their deep dives all figured out. Their flexible carapace, their heart, their blood, their hydrodynamics. But there's one thing about the deep ocean that should be hard for any reptile to survive: the cold. Most sea turtles become cold stunned at around 8 degrees Celsius or 46 degrees Fahrenheit. Their metabolism slows, their muscles fail, and they can lose the ability to swim. I was recently at the Loggerhead Marine Center in Juno Beach, Florida, and many of the turtles in their care are recovering from exactly this. If there's an unusual cold front, many turtles need rescuing. Not leatherbacks though. Leatherbacks have been recorded foraging in waters as cold as 0.4 degrees Celsius, just above freezing. They can be found in waters as far north as Nova Scotia, Ireland, and even Norway. At these latitudes, the ocean can be cold enough to challenge even marine mammals. Yet leatherbacks routinely maintain body temperatures several degrees, sometimes more than 8 degrees Celsius, above the surrounding water. If you remember your basic biology, this should be shocking. Turtles are supposed to be cold-blooded, or more scientifically put, ectothermic, meaning they're animals that rely on their external environment to regulate their body temperature. So how can a leatherback survive the cold like this? There's a few things going on. Beneath their leathery carapace is a thick layer of lipid-rich connective tissue and fat. This acts like a built-in thermal padding, reducing heat loss to the surrounding water, sort of like blubber. They also have a counter-current heat exchange system. Blood vessels in their flippers are arranged so that warm blood flowing outward runs alongside cold blood returning from the extremities. Heat transfers internally before it can escape into the ocean, conserving core warmth. Leatherbacks also maintain higher metabolic rates than most reptiles. Their constant swimming, powered by massive shoulder muscles, generates much more heat than a typical sea turtle would. So are they not really ectothermic? It's complicated. They operate in a thermal space somewhere between classic ectothermy and true endothermy. They're not warm-blooded like mammals, but they are not completely limited by ambient temperature the way most reptiles are either. Tuna and great white sharks are other animals in this mesothermic group, and also maybe dinosaurs. And maybe most importantly, they are huge. Large bodies lose heat more slowly than small ones. A 600-kilogram leatherback has a much lower surface area to volume ratio than a smaller turtle, meaning that heat dissipates far more gradually. Simply being enormous gives them thermal inertia. Once warm, they stay warm. This is also why many cold weather and cold water animals all tend to be huge. And this is crucial for the leatherbacks, not just for surviving deep dives, but for existing at the cold extremes of our planet. Because the cold ocean is where massive blooms of their prey can occur, specifically jellyfish, like the lion's mane jelly, cannonball jellyfish, and moon jellies. Jellyfish like this thrive in the nutrient-dense, oxygen-rich cold water. But this does seem like the worst prey you could evolve to eat. They're made up of 90% water, are very low in fat, and very low in protein. A 10-kilogram lion's mane jellyfish might contain 1,000 calories. A 10-kilogram fish, for comparison, would have more than 20,000 calories. All other sea turtles happily eat things like shrimp or mollusks with much higher calorie density, but not the leatherback. The only thing they eat is jellyfish. So the biggest sea turtle on Earth eats the worst food on Earth? How do they even cultivate so much mass? There's only one answer: They eat a ton.
On a daily basis, our calculations have shown that they're eating about 95 kilograms of food of jellyfish a day, and that's a lot.
To learn more about this, I spoke with Dr. Frank Paladino, a marine turtle expert and professor of biology at Purdue University.
And so they really have to be constantly on the lookout, feeding and finding where the sources are.
And sometimes this takes them to unusual places.
What was really interesting was they were able to swim up against one of the strongest currents in the world, the Agulhas current, that goes between Madagascar and the side of Africa. And they were nest down in South Africa in KwaZulu-Natal, and they actually were able to swim up along the coast right to the opening of the Zambezi River. And everybody thinks that leatherbacks are open ocean pelagic organisms that go out to the eddies where these jellyfish aggregate. But they just sat there for 6 months at the mouth of the Zambezi River, chowing down on the soft-bodied cnidarians that were blooming there because of all the nutrients coming in off the Zambezi River.
So maybe eating jellyfish isn't as bad of a plan as it seems. It works for one main reason.
I think it's because they're so plentiful, and they're one of the few organisms other than the large moa that actually feed on them.
And unlike other predators that need to chase down prey and may or may not succeed at catching it, leatherbacks have a 100% hunting success rate. If they see the jellyfish, they will get the jellyfish. Their beak is perfectly designed to snatch and hold on to their gooey prey. And warning, this is nightmare fuel, but their esophagus is also lined with large, sharply pointed keratin spines. These sharp spines trap any prey that is swallowed and shreds it on the way down. Luckily, their skin is not very sensitive to jellyfish stings, except for their eyes. So every time they're about to chow down, they simply close their eyes. Leatherbacks eat so much jellyfish that when they stop, the ocean starts to spiral out of control.
As a matter of fact, I was brought in by California fishing organizations because they were all upset that now there's lots and lots of jellyfish off the coast of California. As a matter of fact, they're closing beaches and so on. And I went and told them years and years before that they should start using circle hooks on their long lines because they were accidentally bycatching or killing leatherbacks because of the way they were fishing with the long lines and getting hooked on their lines and then drowning. But then they wanted to know why there were so many jellyfish, and then I explained to them they eat 95 kilograms of jellyfish a day, and the jellyfish eat the small fish that are going to grow up to be the big fish that you want to catch. And then they finally, their little light bulb finally went on above their head and they started switching to circle hooks.
And while this was a good move, it hasn't really saved the leatherbacks. But more on this later. Piece by piece, the leatherback starts to make more sense. Its flexible shell helps explain how it survives immense pressure. Its enormous size and strange physiology explain how it survives the cold. And its bizarre jellyfish diet explains why it would evolve to live in these frigid waters in the first place. But one mystery remains. Why dive into the deep ocean at all? A 2008 study started to investigate this question. Researchers analyzed over 26,000 dives from satellite-tagged adult leatherbacks across the North Atlantic. They found that 99.6% of dives were shallower than 300 meters, and only 0.4% exceeded that depth into what they called deep dives between 300 and 1,250 meters. But if leatherbacks are super capable of diving into the deep ocean, why do they only occasionally do it? And what can their behavioral pattern tell us about why they go there at all? The researchers' first hypothesis revolved around predator evasion. Maybe leatherbacks dive deep to escape threats, like sharks and orcas. This would make some sense. Their fleshy shell does leave them somewhat vulnerable to predation from these giant predators. If this were the case, the deep dives would be rapid, short, and occur somewhat randomly. But looking at the diving data, the deep dives normally happened at the same time of day, midday, so not really random. And their descent rate during these dives was actually slower than other dives. That wouldn't really make sense if they were frantically trying to escape an orca. So the predator evasion hypothesis was ruled out. The next hypothesis had to do with thermoregulation. Maybe with those huge heat-generating bodies, maybe these turtles dive into deep water to actually cool down. If this was the case, the turtles' deep dives would correlate with warmer surface conditions and the animals chasing dropping temps. But what the researchers found was that many of these deep dives were much deeper than the thermocline. After about 350 meters, the temperature decreases at a negligible rate, meaning if the turtles were only trying to cool off, they were going much deeper than they needed to. And these dives didn't really correlate with warmer surface temperatures either. So this brought the researchers to their final hypothesis. Maybe they're diving deep to eat their jellyfish prey. Amazingly, these jelly creatures do make vertical daily migrations in the water column. At night, they live at the food-rich surface of the ocean, when light is scarce and most predators can't see them. Then, as the sun rises, they return to the depths, often below 600 meters, where they can't be easily seen by predators. So maybe the leatherbacks are diving super deep to eat this prey. But this doesn't fully explain it either, because leatherbacks can and do simply eat the jellyfish near the surface at night. Okay, these turtles have me stumped. What the heck is going on? Researchers think that these extraordinary and rare deep dives may not be about catching jellyfish necessarily. They may be about finding them. Specifically, finding them when the leatherback has left the richest feeding grounds of the north. One turtle that the scientists had been tracking in a different 2008 study spent more than 2 months lingering west of the Bay of Biscay, circling through a productive patch of ocean and foraging for prey. Then suddenly, it booked it out of there. It kept moving south, and then even more south, until it had traveled all the way from the North Atlantic to the coast of South America. During journeys like this, jellyfish become much more scarce, and researchers think that this creates a problem for the turtles. Leatherbacks tend to travel during the day and feed at night. But by the time night comes, a migrating turtle might be nowhere near a prey patch. So researchers think that while traveling, during midday, the turtles occasionally plunge down into the deep scattering layer to see what's there. Not necessarily to feed, but to scout. If they find signs of a rich patch of gelatinous prey below them, they may remain in the area. Then when night falls and the jellyfish rise towards the surface, feeding becomes much easier. But this all seems complicated and difficult. Why leave the abundant feeding grounds of the north to go look for scraps? Because something more powerful than hunger pulls them across entire oceans, towards the middle latitudes of the planet. Despite everything we've talked about, the insulation, the giant bodies, the ability to survive in freezing northern seas, leatherbacks are still reptiles, and they need warm climates to lay their eggs. That's the force powerful enough to pull a leatherback away from an ocean full of food, a force that eventually draws them back to land. Once they arrive, the females heave their enormous bodies through the sand. They want to lay their eggs beyond the high tide line, so they usually have to travel 15 to 45 meters, or 50 to 100 feet, which is probably pretty grueling. They end up disturbing a huge area on the beach and leave behind long, circling tracks. They then dig a large body pit to lay their eggs in deep egg chambers. They lay up to 100 eggs at a time and lay 4 to 7 nests per season. Once the babies hatch and crawl from the nest to the ocean, they will imprint on this beach. Their brains actively encode their surroundings. This will allow them to return decades later to lay their eggs, a phenomenon known as natal homing. Everyone's familiar with the concept of migration. We know birds make epic journeys across continents, and maybe some people are familiar with whales swimming across oceans. The record whale migration was 9,380 miles, or just over 15,000 kilometers, between Brazil and Australia. But large whales crossing an ocean feels almost expected. They're huge, warm-blooded animals with massive energy stores. But the record-breaking leatherback journey I explained at the start of this video was 20,558 kilometers, or 12,774 miles. No other reptile comes close. No other ocean vertebrate even comes close. So the first question that comes to my mind is, how? How do they do it? How do they know where to go? And how exactly do they know when to leave? The first thing making these huge distances possible are their absolutely enormous flippers. Leatherbacks have the largest front flippers of any living sea turtle, spanning almost 3 meters tip to tip. They're so huge that instead of vigorously paddling, leatherbacks use them to glide, beating them through the water more like wings. With these, leatherbacks can reach very high bursts of speed, up to 22 miles per hour or 35 kilometers per hour, making them the fastest sea turtle. But typical travel speeds are much slower, around 6 miles per hour. Since they have to travel such long distances, they prefer efficient movement over speed. And as far as knowing when to leave, I would have thought it's just about prey availability or dropping water temperatures. But it turns out these aren't great cues for the leatherback. It's something else. And this cute little pink spot on their heads might actually hold an incredible answer. I've been looking at photos of leatherbacks for weeks, and I thought this pink spot was just like a weird blemish. But amazingly, scientists think it might actually be a third eye, or a skylight, which I know sounds crazy, but it's not just the skin here that lacks pigment. The bones beneath it are unusually thin, allowing light to penetrate the skull and reach the pineal gland, a light-sensitive structure deep within the brain. In fact, when researchers shine a light through a leatherback's skull, you can actually see it passing through. So as the days begin to shorten, the pineal gland may help the turtle detect the changing season, providing the cue that it's time to leave its northern feeding grounds. On this graph, you can see that right around the summer equinox, September 23rd or so, the number of turtles in northern waters immediately starts to drop. But this is all still surprising. Even with their efficient swimming and shortening daylight cues to leave, how do they know where to go? To me, the answer almost feels like magic. One explanation starts with a weird crystal made out of the mineral magnetite. Like this, but microscopic. It might help some animals detect something that to us is imperceptible.
They are used as a detection for very fine changes in the magnetic fields of the Earth. And you find those changes are most sensed as you have regions where plates are crashing into each other. What we noticed was there was a definite pattern for the out-migration of leatherbacks. They all kept going out right to the Cocos Islands and then out to the Galapagos Islands, and then they spread out into the South Pacific.
At first, it seemed like the turtles were following the oceanic mountain range, using visual cues. But the mountain range is over a mile deep in the ocean. The turtles wouldn't be able to see it. Instead, Frank's team noticed something intriguing. The migration route closely followed the boundary between two tectonic plates.
They were following the magnetic lines of force, just the same way as birds. If you notice, they migrate along mountain ranges as you come down through Central America, from North America into South America, and then they follow back the same way.
We know sea turtles can detect Earth's magnetic field. Scientists figured this out by sticking hatchling loggerhead turtles in different pools that each had a different magnetic field. Each magnetic field replicated ones found along different locations along their migratory path in the North Atlantic Gyre. The scientists then tracked their position in the pool. Turtles exposed to a field replicating one that exists in the Gulf Stream halfway across the Atlantic, when the turtles would be swimming east, swam east. Those exposed to a field like one found near the northeastern edge of the gyre near Portugal swam south. And turtles exposed to a field like one found near where the gyre turns southwest swam southwest. And the ones exposed to a field that wasn't part of their migration route swam randomly. But exactly how they sense that magnetic information is still debated. Some researchers are holding on to the magnetite crystals as the sensor, but other researchers have a different, tantalizing theory. They think it could be symbiotic magnetic bacteria that are guiding animals like leatherbacks across entire oceans. These bacteria, known as magnetotactic bacteria, produce tiny chains of magnetic crystals inside their cells. The crystals act like microscopic compass needles, naturally aligning with Earth's magnetic field. The idea is that if these bacteria live symbiotically within an animal, they might provide magnetic information to their host, essentially giving the animal a built-in navigation system powered by microbes. It's a fascinating possibility. Scientists have already discovered single-celled organisms that appear to use magnetic bacteria in this way. The magnetic bacteria coat the surface of a protist and cause it to become south-seeking. It always wants to go south. And when the magnetic field was reversed in the lab, the protist immediately changed orientation. And some experiments have hinted that giving birds antibiotics can interfere with navigation. But no one has yet found definitive evidence that turtles use these symbiotic magnetic bacteria to find their way. And we don't really know how the animals would get the information from the bacteria. So for now, the mechanism behind the leatherback's magnetic sense is still largely a mystery. No one teaches the leatherback where to go or when to leave. And yet they move with astonishing precision across thousands of kilometers of open water, returning years later to the beautiful beaches where they once hatched. But unfortunately, people also find these beaches to be too beautiful.
Whenever you have a pristine, beautiful beach, somebody wants to put a hotel with, umbrellas and swimming pools, and some of the best nesting beaches in the world are being taken up because of human development.
Like with most ocean creatures, the leatherback's number one threat is humanity. One of the worst parts about beach development is the never-ending bright white streetlights. Females often avoid these bright beaches entirely. Or if they do lay their eggs, the hatchlings can become catastrophically disoriented when they emerge, heading towards the road instead of to the shimmer of moonlight. And this might be the least of the damaging things humanity has done to these turtles.
Well, the beach where we're focused mostly, it's a national park now in Costa Rica, Parque Marino Las Baulas in Guanacaste on the Pacific coast. For 20 years, they were harvesting all the eggs.
Making this worse is that they actually taste like pee. Leatherbacks and their eggs taste like urea.
They don't have the best in the way of flavor because of the urea aspect. But they were used in bars. They're a big egg, and it was for fertility. You'd suck down a raw egg with a shot of sugarcane rum called guaro, and it was supposed to be an aphrodisiac.
So for a long time, all of the eggs were getting taken. And then eventually, the global fishing industry changed. Long lines became ubiquitous, and then the adults were getting killed too.
And it was only after that when the long lines started becoming an issue. All these older, very mature and experienced females that could live up to 90 to 100 years were getting whacked off, but there weren't any, young females coming into the population. When the two pressures met, the population just crashed. It went from about, I'd say 1,500 nesting females a year down to now we had only 5 last year. 1,500 to 5, and that was in a span of 30 years. So that's a huge crash in the population.
Today, long lines are still used, though they are becoming more restricted in some areas to protect marine life. But is this all too little, too late?
Well, we're doing our best. What is good, though, is we're maintaining it, because now we're seeing new recruits coming in. We're seeing new juveniles being recruited into the nesting population. But then again, people will probably get frustrated because it's going to take a long time for the population to get back. They're going to say, well, the beach is more valuable if we put a Hilton or a whatever hotel right on the beach, and we'll make more revenue that way. But you won't have leatherbacks.
The pressures of capitalism, of tourism, of human nature will always be there. But I really hope that the more science is done, and the more that people learn about these deep-sea giants, that leatherbacks will continue to crisscross the planet for hundreds of millions of years to come. There are few other animals that capture my imagination more. Every time I thought I'd solved one mystery about leatherbacks, another one appeared. Their shell made sense, their deep dives made sense, finally their migrations made sense, and then I found something else that I couldn't make sense of. Every female leatherback lays dozens of eggs that aren't actually eggs. Mixed in with every clutch are these strange, yolkless white spheres. They're not unfertilized eggs, and they're not undeveloped embryos. And as far as we can tell, they're intentionally produced by every female leatherback. And after decades of research, scientists still don't know why. There are several competing hypotheses, but no one's been able to prove which one is correct. I ended up going down that rabbit hole after I had pretty much already finished this main video. So I've written a bonus article that you can read for free over on Patreon that dives into the evidence of each of these theories. All you have to do is sign up as a free member. Patreon is where I'm going to post updates about the channel, about my life, and about any cool animals I might have found that day. I don't always have the ability to make a whole video about something, so this is where all of my overflow thoughts and content will go. Think of it like a free newsletter. You just have to join as a free member. And if you've ever watched my work and want me to be able to keep doing it, there are a few ways to help out financially. At the $5 tier, you'll get access to all of these same updates and get access to a chat room, which is where we've been discussing all of the weird animals and insects that we find, which is so cool because everyone lives in a different part of the world. This tier is really just like a tip jar. And then at the $20 tier, things get more exciting. For each video, I'm making a corresponding glitter and gold limited edition hat pin. So for this video, I've made 150 leatherback turtle pins. So if you sign up to the $20 tier for 2 months, you'll receive one of these limited edition pins sent out personally by me. Think of it like the first $20 pays for the pin and shipping, and the second $20 supports this channel in a huge way. And if you stay signed up, you'll receive a hat pin for every 2 months you're a $20 member. If you signed up before and you're still a member, you'll automatically be signed up to receive this new pin. But I've opened up 50 new spots. I don't know why I love these pins so much, but I just do, and it seems like you guys do too. I have absolutely loved getting your pictures of the pins in the wild. The last run of 100 jumping spider pins sold out in a week. So if you want a leatherback pin and want a spot in this tier, don't wait too long. But if the $20 tier does fill up, I save a few extras for anyone that signs up to the $50 tier or higher. Signing up to get this pin is a massive support to this channel, and you'll get a shiny and cool collector's item. I truly cannot believe how much support the last video got, and you guys have given me so much hope that maybe this is all going to work out. I am so thankful, and it feels like we're building a real community. This is all a big experiment, and there's still a lot of work and a long road ahead, and nothing on YouTube is guaranteed. So your continued support here will mean everything to this channel. So thanks for joining me on this incredible and complicated and amazing and difficult journey to learn about every single organism on this planet.